Greetings and salutations, everybody. This is Jacob. Okay, so how the heck do we tame this beast, you ask? I can't wrap my gray matter around it. Worry not, my friends. By the end of this video, you'll be running circles around this problem. No one will leave this video scratching their heads. Not on my watch. Having that said, though, taming this beast will require us to dive into a new mathematical field. The field of game theory, specifically. So I'm going to issue you a warning from the get-go, my friends. This video is going to be quite definition heavy, since game theory is making its debut on this channel in this video, and I'm not assuming most of my viewers are aware of game theory. So I'm going to have to explain the basic concepts from scratch, my friends. So if a plethora of definitions gives you the heebie-jeebies, then I suggest you take a rain check for today and live to fight another day. In other words, save the video for another day when you're feeling up to the challenge of diving into a new and exciting mathematical field. But if you're feeling up to the challenge today, then I suggest you grab a strong coffee, an espresso preferably, or any coffee that floats your boat for that matter, and brace for impact. But I promise you, it'll be well worth it. Oh yes. So having that said, what is game theory, you ask? Good question. Game theory provides a formal language for the representation and analysis of strategic interactions between entities called players. And these players can be anything really. They can be individual humans or corporations or even microbes. But in the context of most games, what we'll be focusing on mostly will be the strategic interactions of intelligent beings, aka humans, either individuals or groups or corporations. Yes. So now that we know what game theory is, in a nutshell, let's turn our attention to this simple game in order to explain some basic concepts. So we have two players, Bob and Jill, and each of them is being asked to pick one of two balls. Inside one ball is the word split, and inside the other is the word take. Each player is being asked simultaneously whether they're going to take or whether they're going to split. The possible outcomes are as you see here in this table. Each row is labeled with a possible choice for player 1, aka Jill, and each column is labeled with a possible choice for player 2, aka Bob. Each cell in the table corresponds to a possible pair of choices, and the resulting outcome is written inside the cell. So for example, if both Jill and Bob choose take, then neither of them get anything. If Jill chooses to take and Bob splits, then Jill receives $100,000. But this doesn't constitute a complete game because we don't have any information of how the players themselves rank the outcomes. This is what we call a game frame. Here's the formal definition of what a game frame is. And this is a Cartesian product of two sets, for those of you who might not remember. So in order to get a full-blown game, let's have the players rank their outcomes. So let's assume that both players are selfish and greedy. That is, both players exclusively focus on what they themselves get and prefer more money to less. Then Jill would rank the outcomes as follows. Her receiving $100,000 is her number one choice, followed by receiving $50,000. Then last, her receiving nothing. The last two choices are about equal for Jill. The same for Bob. And this is the notation of when a player prefers one outcome to another. We denote it with this fancy inequality thingy here. It looks similar to the standard inequality sign we have in standard algebraic equations. And when two outcomes are about equal in a player's mind, we denote it with this squiggly line here. Oh yes. So far so good. Now moving on. Instead of writing Jill prefers 01 to 02, we can assign a number to each outcome. Let's say 01 equals 5 for Jill, and 02 and 04 equal 2, and 03 equals 10. Of course, 03 being 10 and 01 being 5 doesn't mean 03 is twice as good as 01. And this assignment of numbers to each outcome for each player is called a utility function. And this is the formal definition of the utility function. Of course, saying that for Jill the utility of outcome 1 is 10 is a meaningless statement. It only makes sense when you compare the number to the numbers of the other outcomes. It only matters as long as the utility number of O1 is bigger than the utility number of O2. Beyond that, whether the utility of O1 is 7 or 6 or 10 makes little difference, since all these numbers are greater than the utility of O2. Makes sense so far? And here's the definition of a payoff function. Player I's payoff is a function that maps a strategy profile to the real numbers, as you see here. Let's go back to the table of our initial game. Instead of writing outcomes in each cell, we now write each player's payoff. On the left side of each cell, we write player 1's payoff, and on the right side, we write player 2's payoff. This table is called a strategic form of a game, by the way. So, for example, in the bottom left cell, the outcome for Jill is to receive $100,000. So the payoff for her is 10, which is higher than the payoffs of the other outcomes for Jill. Okay, so now let's move on to the concept of strict and weak dominance of strategies. Let's turn our attention to this game here, represented by this table, where only player 1's payoffs are showing. Let's compare two of player 1's strategies. Let's say A and B. We say that A strictly dominates B if A yields a payoff that is greater than the payoff that B yields, no matter what the other players do. So in our example, A strictly dominates B, since if player 2 chooses strategy E, and 3 is above 2, if player 2 chooses strategy F, and A's payoff is greater than B's payoff, since 2 is greater than 1. And if player 2 chooses strategy G, then A's payoff is again higher than B's payoff, since 1 is greater than 0. We say that strategy A weakly dominates strategy B if A yields a payoff that is greater than or equal to the payoff that strategy B yields, no matter what the other players play. Furthermore, there is at least one strategy profile that makes strategy A yield a higher payoff than strategy B. So looking at our table here, strategy B weakly dominates strategy D, since if player 2 chooses strategy E, then the payoffs are equal between B and D. If player 2 chooses strategy F, then B yields a higher payoff than D. 1 is greater than 0. And if player 2 chooses strategy G, then again the payoffs are equal. Hence B weakly dominates D, since there's at least one strategy profile that makes B yield a higher payoff than D, namely the profile F. And here's a formal definition of strict and weak dominance. And we say that A is a strictly dominant strategy if A strictly dominates every other strategy of player I, and A is a weakly dominant strategy if for every other strategy X of player I, one of the following is true. Either A weakly dominates X or A is equivalent to X. Now moving on to the strict dominant strategy profile and weak dominant strategy profile. This is the formal definition of these two concepts. If in a game a player has a strictly or weakly dominant strategy, then a player ought to choose that strategy. Unfortunately, games that have a dominant strategy profile or solution are not very common. What should a player do when she doesn't have a dominant strategy? What should they do? And here's a definition of the iterated deletion of strictly dominant strategies procedure. The game in this table illustrates this procedure. Notice that H is strictly dominated by G for player 2. 1 is better than 0, 2 is better than 1, 1 is better than 0, and 3 is better than 1. So we delete H from the game, and this is the resulting game. Now comparing strategy C with D for player 1, we conclude that C strictly dominates D, and so we delete this row from the game, and the resulting game is this one. And we notice in this game that F strictly dominates G, so we delete the G column. And we repeat this process until we're left with a game that has no strictly dominated strategies. This one right here. Player 1 has strategies A and B, and player 2 has E and F. This game is called the output of the iterated deletion of strictly dominated strategies procedure, or IDSDS in short. As you can see, there are 4 strategy profiles, not just one. So there's no dominant strategy solution. Let's move on now to the iterated deletion of weakly dominated strategies, or IDWDS. It's basically the same thing with the IDSDS, only this time we're dealing with weakly dominated strategies. But unlike IDSDS, here the order in which we delete strategies matters. So we can end up with a different output depending on the order of deletion. Let's illustrate this with an example. So we have this game right here. Since M is strictly dominated by T for player 1, weak dominance includes strict dominance, by the way. We delete it and obtain the reduced game, as you see here. Now L is weakly dominated by R for player 2. So we delete this column and we're reduced to this game. Now A and B are strictly dominated by T. Deleting them, we are left with a strategy profile, TR, with corresponding payoffs, 2 and 2. Going back to our initial game, let's change the order of deletion and see what happens. Notice that B is strictly dominated by T. We delete B and are left with this reduced game. Oh, yes. Now R is weakly dominated by L for player 2. Deleting R, we're left with this reduced game. Now T and M are strictly dominated by A, and deleting them leads to A, L with corresponding payoffs 4, 0. So we ended up with a different output this time. So here's the strict definition of the IDWDS procedure algorithm. In order to avoid this problem, at each step we identify and delete all the weakly dominated strategies of each player all at once, as you see here. So far, so good? Okay, so now let's switch gears and define what dynamic games are, a subclass of which are perfect information games. Often interactions are not simultaneous, but sequential. Players take turns making moves instead of simultaneously. Chess is one such game. Checkers, tic-tac-toe, etc. Games with sequential interaction are called dynamic games, or games in extensive form. Perfect information games are represented by rooted directed trees. Here's a formal definition of a rooted directed tree. Perfect information games are games in which every player knows all the past moves of every other player. And here's the definition of a finite extensive form with perfect information. Just like in the case where players make moves simultaneously, like in the first example of this video, we don't have a full-blown game with perfect information unless we have a preference of the players for the outcomes. So now this is the definition of a finite extensive game with perfect information. So we'll illustrate this with an example. Here we have an extensive form of a perfect information game with the nodes and the arrows. Under the terminal nodes, we have the payoffs for each player. The first number is the payoff for player 1, the middle number is player 2's payoff, and the last is player 3's payoff. The first node is player 1's starting node. She can either choose strategy A or B, and here we'll explain the notion of strategy in a perfect information game. A strategy for a player in a perfect information game is a list of choices, one for each decision node of that player. For example, suppose that player 1 has 3 decision nodes in a given game. At one node, she has 3 possible choices. At another node, she has 2 possible choices. And at the third node, she has 4 possible choices. Then a strategy for player 1 in that game can be thought of as a way of filling in 3 blanks. Since there are 3 choices for the first blank, 2 for the second, and 4 for the third, the total number of possible strategies for player 1 in this case would be 3 times 2 times 4 equals 24. One strategy is A2, B1, C1. Another is A1, B2, C4. and a strategy for each player involves redundancies. For example, in the game we have here, even if player 1 intends to play A on the first move, she still has a plan on what she'll do if she plays B. So a possible strategy for player 1 is A, G, and another is A, H, and another is B, H, and another is B, G. 4 in total. Makes sense so far? So now let's cover the notion of an imperfect information game. Unlike the perfect information game, an imperfect information game is a game where the players only have partial information about the previous moves of the other players. Let's give an example to illustrate this. Say we have the following game. There are 3 players, Anne, Bob, and Carla. Initially, Anne and Bob are in the same room, and Carla is outside the room. Anne moves first, chooses either a red card or a black card from a full deck of cards, shows it to Bob, and puts it face down on the table. Now Carla enters the room, and Bob makes a statement to Carla. He either says Anne chose a red card, or he says Anne chose a black card. Bob could be lying, or he could be telling the truth. After hearing Bob's statement, Carla guesses the color of the card that was picked by Anne. The card is then turned, and if Carla's guess was correct, then Anne and Bob give $1 each to Carla. Otherwise, Carla gives $1 to each of Anne and Bob. The extensive form is shown in this tree here. So what is this rectangle enclosing 2 of Carla's nodes, you ask? These are what we call information sets. Information sets are sets of nodes where a player has the same information about the other player's previous moves. For example, one information set for Carla is where Bob announces red, but she doesn't know whether he's lying or not. The other information set for Carla is when Bob announces black, and again she doesn't know if he's lying or not. So since Carla has 2 information sets and 2 choices at each set, then she has 4 strategies total. 2 times 2 equals 4. So in an imperfect information game, the total amount of strategies a player has is given by this formula here. Choices at each information set to the power of the cardinality of the information sets. That is the number of information sets. And this is the formal definition of an information set, my friends. Yes. Now let's move on to the notion of chance moves. So far, we've only considered games where the outcomes don't involve any uncertainty. Let's illustrate this with an example. There are 3 cards, 1 black and 2 red. They are shuffled well and put face down on the table. Adele picks the top card, looks at it without showing it to Ben, and then tells Ben either the top card is black or the top card is red. She could be telling the truth, or she could be lying. Ben then has to guess the true color of the top card. If he guesses correctly, then he gets $9 from Adele. Otherwise, he gives her $9. How can we represent this situation? Whether the top card is black or red is not the outcome of a player's decision, but the outcome of a random event, namely the shuffling of the cards. In order to capture this random event, we introduce a fictitious player called nature or chance. In other words, we shoehorn nature as a player in this game, even though they're not a real player. And we assign a probability distribution to nature's choices. In this case, since 1 card is black and the other 2 are red, the probability that the top card is black is 1/3, and the probability that the top card is red is 2/3. Notice we don't assign any payoffs to this fictitious character called nature, because they're not a real player, as we said. Only Adele and Ben are the real players. We depict this situation in the following diagram. So in this diagram, we directed the arrows in a crisscrossed manner instead of the square manner. The numbers we see under the terminal nodes are outcomes and not payoffs, by the way. So how do we calculate payoffs when probabilistic outcomes are involved? The following definitions will help us in this regard. Probabilistic outcomes are what we call lotteries, and the player is said to be risk neutral if she considers a money lottery to be just as good as its expected value. Hence, a risk-neutral person ranks money lotteries according to their expected value, And here's a strategic form of the game where the numbers in the cells are the payoffs, which is the expected value of the money lotteries, since both players are risk neutral. So far, so good? Everybody good? So having said all that, at long last, now that we're armed to the teeth with all this theory, now we're ready to kick this problem's teeth in. Ooh-ees. The problem in the thumbnail, that is, it's going down. It'll be pushing up daisies pretty soon, my friends. Ooh-ees. So moving on to our puzzle problem at hand, let's depict Yvonne's and Zoe's situation with the following diagram. Here's the diagram, or the extensive form, or the directed tree, whatever you want to call it, using a combination of the crisscross and square method. Sometimes things just get too messy using purely the crisscross method, because too many arrows sometimes might cross paths and it might get confusing, so you have to use a bit of both methods, my friends. So the numbers at the terminal points are the outcomes, not the payoffs. For example, if Yvonne receives card A and Zoe receives card B, and Yvonne bets and Zoe sees, then Yvonne receives $2 and Zoe loses $2. So how do we calculate the payoffs? By using the formula we just gave with a mathematical expectation of the money lotteries. First of all, since each player has 3 information sets and 2 options at each set, then Yvonne and Zoe each have 8 strategies, correct? So this is the strategic form of the game, and slowly we'll fill in the cells with the payoffs. So let's start with the first cell, where each player folds no matter what card they receive. So the payoff for Yvonne in the pass strategy is 1 times 1/6 plus 1 times 1/6 plus -1 times 1/6 plus 1 times 1/6 plus -1 times 1/6 plus -1 times 1/6, which equals 0. In the pass bet and pass strategy profile, Yvonne's payoff is 1 times 1/6 plus 1 times 1/6 plus -1 times 1/6 plus 1 times 1/6 plus 1 times 1/6 plus 1 times 1/6 equals 4/6, which is 2/3. Zoe's payoff is the exact opposite, so 2/3 and -2/3. The 1/6 represents the probability of Yvonne receiving one card and Zoe the other, if you're wondering about that. So the payoffs is the sum of the products of the outcomes with the probabilities of the players receiving the cards that they get. So we fill in the table using this formula and we get these payoffs here. So now what do? We apply the IDWDS procedure on this game. That's what we do. Yes. So like we said earlier in this video, in the IDWDS procedure, we delete all the weakly dominated strategies of each player in the same step. So for each player, we have to compare 28 pairs of strategies. So we go through each pair one by one, and slowly but surely we compare all the pairs of strategies for both players, and we conclude that the strategies pass, bet, pass, and pass, bet are weakly dominated for Yvonne. So we delete those all in one go. Zoe has 6 weakly dominated strategies, namely fold, C, fold, C, fold, C, fold, C, and C. So we delete these in one go, and we're left with the game here. Here we only have 6 pairs of strategies to compare for Yvonne, and 1 pair for Zoe. So the weakly dominated strategies during the second step for Yvonne are bet, pass, and bet, and we delete those, and we're left with this reduced game with 2 strategies for each player. And this reduced game is the output of the IDWDS procedure. Hence, these are the strategies that each player should employ during the game. Namely, Yvonne should either bet when she has the A card and pass when she has the other cards, or she should bet when she has either the A card or the C card and pass when she has the B card. And Zoe should either C when she has the A card and fold with the other cards, or C when she has the A or B card and fold with the C card. And that's all she wrote, my friends. That's your answer. Ooh, yes. Wow. Just wow, you guys. Was that a problem or was it not? Quite a spectacle of a problem. I'm going to be honest with you guys and gals. This was a difficult video to make, not because of the length of the video, but because I had to make decisions on what to include and what not to. Unlike with my calculus or algebra videos, for example, I assume you have some familiarity and or have taken a course about these topics. Here I assume you had no prior exposure to game theory whatsoever. I don't even assume that you've even heard about this mathematical field at all, my friends, which is a logical assumption, of course. So I had to build everything up from scratch. So it was a monumental undertaking for me, especially since I myself only started dabbling in game theory a few weeks ago. So you can imagine the bewilderment and pressure I felt during making this video. It's no walk in the park to start teaching something you yourself learned 2-3 weeks ago. Oh no. But you know what they say, if you want to learn something, start teaching it. You can be dabbling in something for decades, but unless you start teaching it to others, you won't achieve a true mastery of it. I'm a firm believer of this philosophy, my friends. But of course, I'm not complaining, you know. Game theory has certainly exceeded my expectations on how interesting and useful it is. It has widespread applications to the sciences, to modern economic theory, to all sorts of things, international trade, auctions, antitrust lawsuits, things like that, legal stuff, even to biology, you know. If you're an applied mathematician, then game theory is certainly the field for you, my friend, that you should be dabbling in. Oh yes. So that being said, let me know if you like this puzzle, if you found it difficult. I mean, if you're not familiar with game theory, then of course you'll find this difficult. Let me know if you like this category at all. I wanted to debut the concept of Nash equilibrium as well, but decided against it, since this isn't the best example to explain the notion, since this game in particular has no Nash equilibria. I'll probably introduce it in the next video about game theory. As always, smash those buttons like they owe you money. Share any suggestions you might have. And I'll see you guys in the next video. Bye-bye.